Well, this is my basic, the basic idea. We have statistics currently in the form of most common value list, which is basically this, which is by default the 100 most common values. And could you? Yeah. The default of 100 most common values. This works just fine in general, but when you are going to filter on more than one column, the statistics don't provide a very good sense of cross-column statistics, because in general, if I have the zip code of city and the city both in my columns, then the one implies the other as well. But our statistics don't show that by default. You can add custom statistics through the create statistics statement, but that adds manual interventions that we could potentially prevent by using specific kinds of statistics, generally called sketches. Let's see. So that is what I was. That is what I had suggested last week, I guess, on the hackers list. Initially, this could be done through hyperlog sketches. They provide some coordination, but no. I lost the word for it. It allows you to determine where in it adds some information on where in the table a tuple with that value is, and it allows you to combine the statistics between two columns without a loss of accuracy, so that the default of A plus B is not just BA times BB, but the actual correlation of these two values due to the combined locality information that is embedded into the hyperlog log sketch. An alternative sketch would be the Tata sketch, but we discussed after some research that was it is limited by license. I realized because it's under the Apache license, which does not transitively give you a license to also license the covered patents to other people. And also in the non most common value list cases, Thomas suggested to you to also improve the statistics for these values by using the, what's it called again? Count min sketches, which also provide some amount of accurate value counts for your distinct values, and it allows you to make more and more accurate join estimates, even between columns and tables. That's basically it. I was, there are some issues with either, and I'm not sure on how licensing works within Postgres or the Postgres community, how we want to how compliance with, for instance, Apache license works. I'm not 100% on that.
Apache license would be a license for code, but would we be using anybody's code or just implementing algorithms ourselves?
There is this library in C++ called the data sketches
I see.
framework. I'll put it up in my notes. Yeah. Which has data sketch, and that is quite accurate, but I'm not sure on how especially I'll grab the link on a message from Bruce, I believe, about how some licenses are not exactly useful.
So,
but yeah,
we have features that can use external libraries that are licensed differently, like readline. But I suspect, like, if this was a generic feature that allowed sketches implemented by a library, and then you had a contrib module that used this, or even a compile time option that added support for this particular sketch, but it was useful for others, then that might be okay. But I suspect if the feature was entirely dependent on this library, then I suspect it would.
So I think there are two things, right? One thing is the code, and I guess it would be easier enough to re-implement the sketch, because inherently all the sketches are fairly simple, right, code-wise.
Okay.
So that would be simple. I think what Matthias mentioned is
patents.
More complicated is the patents, right?
Yeah.
I have no idea. I mean, like I know that Apache license has a patent grant, but I have no idea how that works for this particular sketch. I think that's mostly like irrelevant, right? I mean, like I think this shouldn't be a session about patents and licensing. I think there are other sketches that might be actually useful. So maybe let's not go.
The usual recommendation is not to go looking for patents. If you think there's even a possibility of it being patent encumbered, we probably would like stay very far away.
Yes, I mean that was my idea too. I think there are other sketches that might actually work for our use case, because most of these sketches, definitely hyperlog, countmin, and so on, are designed for streaming applications, right? So the assumption there is that you essentially pass all the data through that, right? So it needs to scale perfectly fine for like billions of records. But that's not what we are dealing with here, right? We are only building the statistics on like a small subset of the data. It's like 30,000 rows by default, or maybe like up to 3 million rows. So even the simpler sketches should actually handle that just fine, right?
Yes.
So we don't need like the state-of-the-art sketches as long as they are sufficiently accurate. I think there are other sketches that we could look at, like for example Bloom filter, which is like extremely simple, but it actually gives pretty good estimates for intersections and so on. Did everyone actually understand like the idea of what Matthias was talking about, like how actually this would work?
I have a question, which is, I'm not clear how the HLL sketch is better than our current, like cross-column statistics in that I don't, is he going,
Right.
are we going to have sketches for every possible pair of columns? Like, does it
So,
answer the question
no.
for every possible pair?
So the whole idea is that you actually don't need to build cross-column statistics, right? So you would have sketches for values in one column, and then you have sketches for values in the other column. Like imagine like most common value lists, but instead of frequency, you would have a sketch for rows with that value, right? That tells you essentially which rows in the sample had this value. And then when you have a query with with conditions on both columns, you could actually combine the two sketches from the two statistics, right? So you would essentially do like an intersection of the two sketches. And then
exactly, because the sketches have encoded within them the locality of each tuple containing that value. You can combine them, and the combination of those sketches then provides you with the information of whether there are tuples that in the sample set that actually contain the combination of those values, and how many of those there are.
So, Greg, this is where I got lost too. And I got, Tomas, thanks for the email this morning. I was looking at it. And what it appears it does is it takes, let's say, the 100 most common values, right? And it makes a sketch for each one. But instead of just doing the value, it's doing the sketch of the value and the TID of the row. So there's like this long, so each unique value has this sketch, which is kind of like a map of the TIDs that apply to that common value, right? And what I'm understanding relatively is that you can take a column, another column from the table, and somehow these two sketches, you can merge them on top of each other and figure out how common it is that the row has both of these values in it.
I mean,
yeah.
If you want to make it extremely simple, just imagine that the sketch is the list of the IDs for each value, right? I mean, that's the simplest sketch, which is very easy to work with. And it would actually, I'm thinking, extremely cheap to store, right? Because it's only like 6 bytes per.
I was about to point out you could then implement that as a bitmap, so 1 bit per block rate, and then you've described a bitmap index.
Right. So, but that's exactly true. I mean, like you would have 1 bit for each row in the sample, and you could actually combine those bitmaps, right? And inherently, most of the bitmaps, because if you have many different values, then most of the bitmaps will be extremely sparse, right? I mean, like because there will be like very few bits set for each value, and you could actually combine them very cheaply and compress that. So maybe instead of like looking at those, state-of-the-art sketches, we should actually think about something like this, like extremely simple, but which actually doesn't lose the information about the exact TID, which we don't.
What I was getting at with my comment is that there seems to be a bit of a gray, like the more information we put in the statistics, the more they look like another index. And the flip side is the more flexible, like the more our indexes implement things like Brin indexes and bitmap indexes and things like that, the more they start looking like statistics. And I wonder if they're like.
I don't think so. I mean, like this doesn't look like an index at all, and I don't think it's like a bitmap index at all, because we are only dealing with like a small sample, and we are keeping the information that allows us to combine the statistics for different columns. So I don't think that's a problem here. Obviously, like as you are making the statistics more and more accurate, right? Ultimately, you would get like the total data set because that's the perfect approximation. But I don't think that's what we are doing here.
No, I see what you're saying now. That doesn't make sense because you'd be able to know, okay, this one has this many bits, this one has this many bits. And then what you're also going to find out is how many common bits are between the two of them, right? And that's your correlation.
Or with the first of all, I don't think this size is huge. Actually, I think the size is actually pretty small.
Well, this would be on the order of 300. 300 times a sample. Statistics value, at least for each value, because every bit for each sampled value.
Yes, I mean you would have like 300 times the sample size in bits, so it's only like 8 divided by 8. But also most of the bitmaps will be sparse, so that will be easy to compress by run-like encoding or something, right? So I think it wouldn't be that bad, but we can. I think that the question is like how beneficial this is and how it compares to the more elaborate sketches, right?
So, what order of magnitude size are you aiming? Well, I mean, I guess that. So, if it was a Bloom filter, for example,
the point with most probabilistic sketches are that they are accurate on something like you need something in the order of 1,000 buckets.
Right, but you need that actually per value, right?
Yes.
And the bitmap here is actually the total bitmap for all the values, essentially, right? So,
well, the samples, so the values in the sample, or if you're doing something like HLL, the values that are HLL tries to take a certain percentage of the discrete of the different values.
I mean, like within like 1.5 kilobytes, you can aggregate into hyperlog like billions of rows, right? So that's fine. I mean, like we are only dealing with maybe 3 million rows total. So we could probably do with like 200 or 300 200 bytes per value.
That is a misestimation. Hyperlog uses those 1,500 bytes to provide estimates within 2% of the actual values.
Right.
So I think the number that's relevant isn't the number of rows; it's the number of distinct values. So if you have 3 billion, but if you have 3 million rows, but there are 3 million distinct values, but some of them are not.
Oh yeah.
Common, I mean, like, then you have a problem.
Yeah, but in our case, we would be feeding like tuple IDs, right? So they would be unique for each row. So there's no difference. Because we are essentially, we need to treat each row as a unique value, right? Because selectivity works on number of rows.
Yes.
I don't see how you use HLL then.
You use HLL to encode the locality of your tuples so that you can combine the locality of another column's statistics to get accurate values.
Yeah, I think we shouldn't really be talking about hyperlog here. I think that's like overly complex. Maybe we should be sticking to like a simple sketch, which is like just the list of tuples or like the bitmap of tuples within the sample or something like that, because that makes it much easier to actually talk about intersections and or
Yes.
unions, right? Which is what we need to use for to estimate selectivities of and or clauses.
And Tomas, as I understand it, like you don't need the TID. It's just like the first bit is the first row we sampled. We don't really care where it is, right?
Yeah, I mean, like,
Yes.
I mean, the TID is just like a way to get unique values for each rows, right? I mean, like, that's it.
Right, but we wouldn't put that in the map because we just
No,
say the
but-
first row we sampled, it has either it's on or off, right?
Yeah, sure.
Yeah.
Once you switch to the bitmap, we could use just like a position in the sample or something.
Right, because I guess my point is that every column, the first bit would always represent the first row we sampled. Right,
Yeah.
because we don't sample different columns with different rows. It would, we take the first row, we sample all the columns, right? And then the
Yeah.
second row, we sample all the columns, right?
Well, we could actually sample, if you do that explicitly, we do sample like different columns by different.
Oh, you're right. We have different target. Yeah.
No, I mean, like, different targets are irrelevant here, because then we use the largest one and then we just build the statistics differently. What I'm talking that you can actually do analyze and list the columns that should be analyzed at that
Oh,
time.
I forgot about that. Okay, that's a good point.
Can you
Okay.
describe the bitmap data structure? I'm trying to wrap my head around.
I mean, like,
How would you use it?
How would you what?
So,
Greg?
okay, so you take a sample of rows,
Yeah.
and in that sample of rows, you look at that you
So
make a
for
bucket,
example-
an object for each distinct value, and in that object you store a list of positions for where you found it in the sample.
So for example, let's say the first column is a city name, right? So you would have a Prague, and then you would have a bitmap of which rows actually contain Prague.
Which rows from your sample?
Yes, from the sample, right? Then you would have a different city that would have a different bitmap and so on. Ultimately, if you combine all these rows or all these bitmaps, you would get like just ones, right? But they are like exclusively.
Because
and then-
Greg, the problem is right now, if we have a value in column A that's 10% and a value column B that's 10%, we assume it's a 1%, right?
Right.
But we don't know. Maybe it's 9%, maybe it's 0.01%, right? Because we don't have that correlation. We just assume they're independent. I think what they're saying, which
how do you use, so with this data structure, if I now search for Montreal and Montreal wasn't in your sample, do you have
no
any idea?
I mean, sorry, but we can't actually help, right? Because
Okay.
we have the same problem with say the most common value list in general, right? I mean, like, if the value doesn't make it into the most common value list, I mean, like, right. Sorry, but
so with the sketch, then we would know. Oh, okay. So
and
we
then you have
know that Montreal is 10%.
Right.
But with the sketch, we can combine it with the sketch for another value and know what
for another column,
sample.
right? For another column.
Yes.
And
We would know what percentage of the sample had both those values.
right. So Montreal, Canada is the good one, right? So you know, maybe Canada is 15% and Montreal is 5%, right? And what we do now is we multiply them together and we get like 0.5%, right? But if you do it with this, you take Montreal, you add the bits with Canada, and you find you get 5% because every Montreal is in Canada, right? Now that's what Tomas's, statistics per column group do. but this does it more automatically without having to separate them out.
Right. And I think
Predefine
like
them.
You still might not want this on every column.
right.
Like if
I mean,
these, if these are, if you have a real need for this, you might really want them to be relatively large because you're really relying on these estimates. And so you might want to, if they're going to be several kilobytes or even tens of kilobytes, you might want to be able to say, look, these are the 3 columns, 5 columns that we want sketches on. We have a 500 columns in this table. We don't need sketches on all of them.
yeah, probably. I think I can imagine like cases where it doesn't make sense to have these statistics. Like most OLTP workloads probably won't have this issue, right? Because they are only dealing with like point queries or something. But then you will get to workloads where this could be actually quite beneficial. And at that point, you are willing to spend the extra disk space or like CPU time to actually build and maintain this. And I can imagine doing something like we do for expression statistics, right? Where we use the extended statistics interface to also build statistics on expressions. So you could also say, for these columns, also build this extra, most common value list with sketches. That would work.
Yes.
So I think I wouldn't really worry about the size too much. I mean, like, even if it's larger, if it's something you only enable when you actually get the real benefit from that, I think that's perfectly fine.
Yeah. Yes, and also on the list I had. Okay, on the list I had the other ID is our current sampling for statistics is fully random, basically. And I shared that we should, if we're going to do this, it's highly probable that we also want more accurate cross-run statistics.
I think you might need a property of HLL, which is what I was getting at before, which is that it doesn't sample a sample of the rows. It samples a sample of the values. The idea with HLL is you gather all the values, and when that becomes too many, you discard half the values by discarding from the hash space. So you keep gathering exact counts for the values that you're still gathering, for the sample of values that you're keeping, because otherwise you're
So I'm not quite sure. First, I'm not sure hyperlog is the right sketch to do this,
No,
right? Because of the accuracy, right? And second thing is, I'm not sure why would we actually need to modify the sampling to be deterministic, because as long as we sample all the columns that we use to combine stuff, I think that's fine. So, for example, we could, for example,
I think you're right.
Right.
I think you're right, because if you're answering the question of how selective is city equals this and country equals that, that's a percentage of the table. That's the kind of that's the kind of answer that our existing sampling should be the right kind of sampling.
Right.
What hyperlog is trying to answer is how many distinct values will you find in this set? And
I
that's a
think,
very different kind of question.
right. I think the problem Matthias is trying to solve is that you could actually sample different columns at different times, at which point the bitmaps will not match, right?
Mhm.
But I'm not sure the deterministic sampling would actually fix that, right? Because you would essentially need to scan the whole table and sample, for example, data based on like a hash table or something based on
But we
that.
don't do that, do we?
No.
When we sample, we use the whole row when we look at it.
Right. I mean, I'm not sure we need the deterministic sampling, and I'm not sure. Maybe I just don't see the problem. But I also don't think the deterministic sampling would work because of the activity that can be between like analyzing different columns. So maybe I'm just like completely missing the point. I'm not sure. So Matthias, what do you think would be the right algorithm or something, or what features would the sampling have to have?
For bitmaps, it would be important that you do all of it at once, because you need the mapping to the tuple ID, which doesn't exist in bitmap. For hyperlog, and datasketch, the sampling should be deterministic, because long as many as possible TIDs are the same between the samplings, you will retain some of the correlation between the two columns, because the sketches are made on approximately the same data sets, as long as some amount of correlation between the table size remains.
Yeah, but right. So when you say deterministic, I mean, we probably don't need like deterministic sampling at all if we always sample the whole, all the columns, right, at the same time. I mean, like that works for all sketches essentially.
Yes.
Right.
Yes.
So I think it would be fine to assume that this happens, and if it doesn't happen, then don't build this type of statistics or something like that. I mean, I have the restriction initially like this.
Yeah, that could work.
I think that's for like initial implementation just fine, because
yes.
As a code comment, the sampling and the statistics analysis are very different parts of the code. Like it would be kind of hard for to make one of them depend on the way the other one worked.
Yeah.
But at the same time, it's quite easy to alter the way we sample the table, because it's only that one piece of code that we have to change.
If you wanted to do it all the time.
Right. I think we already have like a lot of, I don't say issues, but sampling is definitely not cheap at this point. I mean, like it's not entirely random, right? Because we first scan the first, I don't know how many blocks, and then we do like a replacement of the existing rows, following the Knud's algorithm. I think it's the S or something. So, and there are actually weaknesses in that, right? I mean, like once some of the blocks are more populated or less populated or something, it makes it more or less likely that the rows from the block will be sampled. So, yeah. But I think I would keep this like a completely separate thing.
Yeah, I can see why. Yeah.
I missed the point you made in the notes if you want to add it later.
Which node?
The I put it in the chat.
Okay.
I see Matthias is also keeping his notes, so it's
Okay.
fine. If this isn't useful, that's fine. I'm not upset.
Yeah, this is a copy of my working document on things I think can be changed in Postgres. So, yeah. Yeah, where were we? Yeah. But yes, I think we have at least sketches provide some value. Another good benefit that I think exists with these sketches is that it allows you to also combine them while working up the inheritance tree. I'm not sure that is actually something that you can do with other kinds of sketches.
So I haven't really thought about this, but I think that might work. But that's probably what makes the
Can't
the sampling like more problematic, right? I mean, like, because what I think we do now is we will resample the tables once we go to the inheritance tree, right? I mean, like,
Yes.
right. So doesn't that actually go against the idea, or?
Yes, partially. You will indeed have the problem of skewed statistics once one of the tables is much larger than the other, because you, as they are right now, your statistics would be matched 1-to-1 that of size versus size.
I mean, we would know what the sizes were. Can't you consider them proportionally?
No, not with hyperlog, not with data sketch, and bitmap would also not work that way, because you have a sample. These are sketches on the sample size of whatever amount you did sample in the table. You can't just add more values, or dropping values is also not possible, or at least not possible under HLL and theta.
I guess my question. I mean, wouldn't you calculate the selectivity of them separately and multiply by the size and then add up your results instead of
yes,
combining
but
the
that
sketches?
is at the planner. Yes, but that is in the planner. That is not in the statistics itself on the table. Because
some parts of the optimizer actually do work with the parent, and some parts actually do work with the individual children, right? It depends on like the exact location. I'm not sure if it matters for this statistics, but for example, for group by, that actually does matter. When estimating like aggregation or grouping. But I'm wondering how this work, like modifying the sampling, how would that work for foreign tables, for example? I mean, like, can we even make that like deterministic, or what would that work? How would that work? I'm not sure. I think sampling in general is like pretty complicated, and we have a lot of issues with that in practice, exactly because, for example, we do sample when sampling foreign tables. That's pretty terrible. I think we are like reading all the data or something. I'm not sure.
I'm still not. I mean, I'm using the simple sketch that you described in my head. So if you just had a bitmap or list of sample elements that had the desired value, and you wanted to combine up the inheritance tree, you would have to store a weight. So like each sample would be in or not in, like have the given value or not, and represent some number of rows. And then when you go through your sketch, you'd be comparing like all the ones that say Montreal and all the ones that say Canada, and looking at each sample in there, and instead of just having a 1 or a 0, it would have a magnitude, and you would add those up. And it wouldn't necessarily need to store that in the sketches on disk, just in the sketch, like when you're combining them into an in-memory representation oh, I see. I guess I see what you mean. You're trying to store a combined sketch for the inherited table, for the parent
Yes.
table, and you want to store that combined sketch in the same format that just represents samples.
Yes.
So you would either need like an enhanced one where the samples have a magnitude attached, or you would need to like insert duplicate samples or something. But it seems like it might be. And then you would have a bit. Well, I guess it wouldn't really be a problem. Different elements of the inherited table might be sampled at different times, but they don't need to be at the same time for that to work. I mean, it feels like this is a thing that could be made to work. It might just be expensive. It might not be practical, but
22.
Yeah, it can definitely be made to work. Probably sampling a proportional first and entries between the inherited, the child's tables. It could be made to work, but I'm not sure on the representativeness of the resulting set.
I think you're talking about a different solution.
That might be.
I was just like describing, like if you were just to do it the naive way of weighting each child table sketch, like by the size of the table, how like you would, in the resulting combined sketch for the inherited table, each sample, like instead of a bitmap, instead of 1 bit per sample, you'd have to store a magnitude for each
Yes.
thing, like how many rows it actually represented, and that would make it larger, but it's not actually impossible to make that work. It's just, I'm not sure whether it would be practical.
Yeah, it would probably be not at all practical, because then you'd have to add at least a weight for every subtable, which becomes quite expensive quite fast once you go to a lot of subtables.
Well, I guess, wouldn't you keep... Oh, is this what you were saying? You would keep only some of the samples from each child?
Yes.
So you would keep a different number of samples from each child based on the relative sizes.
Yes. And then that
I've
would
caught
be
up.
somehow
Okay,
representative.
I've caught up to you now. I'm sorry.
Yes. So you'd still have the normal size, assuming that the statistics target for the parent is small enough that all the children can fill it.
I think we're getting an echo from Thomas's room. If you could mute when you're not talking, that might help. Thomas?
What?
I think we're getting an echo from your room when Matthias is talking.
Yeah. I think that's better, yes. So yeah. What were we about? Where were we again?
Well, I just caught up to you on how you would combine
Okay.
samples for children. I'm not sure that helps you much, but it helps me.
Yes.
I think I agree with Thomas that looking at theta or HLL, like the way to approach this, I think, would be to use a very simple data structure first, and then
Yes.
see how it what problems you have, because the different optimized data structures are solving different problems. So you'd want to know what problems you really have in Postgres before you start trying to solve them. Like I'm in particular, I mean, I don't know anything about theta, but I know HLL is specifically solving the problem of answering a different kind of statistics question, which is the number of distinct values. And I don't think it's actually that useful for answering the question, the normal selectivity questions. I think like the next step up from a simple bitmap or list would be a Bloom filter.
Yes. I thought about that as well, but the main point of using the HLL was, at least at that point, that you can accurately combine them while maintaining that if the rows were not distinct, that is, if all A also imply all B, then combining the two sketches will result in the same sketch, and therefore that the row count won't change. That was the main idea, because that allows for much more accurate of the PA plus B is not equal to PA times PB.
Well, I'm not actually sure about this, because the hyperlog is accurate for the count distinct, right? But once
Yes.
you need to do intersection,
Yes.
you need to do, I mean, like that's actually a problem, right? Because then it's not really as accurate, right? So I think I certainly agree with what was proposed, like using the simplest possible structure, like even the
Yes.
bitmap, because it's very simple and we exactly understand like what's happening, and it's kind of difficult to do that for hyperlog and all
Yes.
these analytic structures. So
yes, hyperlog itself, I also, after the research of what kind of sketches do exist, I indeed also found out that hyperlog is not a great idea if you want to do intersections, unions, and A implies B relationships. In that regard, Theta has better combinatory options. Bitmap is even better, but and exact, but has the limited sample count issue, because it is linear in the amount of samples that you put into it. That doesn't have to be an issue in our case, because we have only 3 million rows in the worst case. But if we want to do larger sample sets, which is not unlikely for the analytics workload, then we should, then there would be the option for other kinds of sketches. And Theta sketch is a good one in that case.
But like I said, I'm not even sure HLL is answering the question you need to answer. It's telling you the number of distinct values. I don't think you can answer the number of rows that are going to be in the result the way you want.
Well, if the value that you are adding to the hyperlog is the ID, the row ID essentially, then you get the right. Then it actually is giving you the answer, right? Because
Then you're just
it's, or you could just feed in the position, like
but then you're just taking a sample of those TIDs, like a 1/2 to the n of the TIDs, and you'd be much better off with a Bloom filter where you're actually you're getting more than one sample per bit in the Bloom filter. But like I think it's not using HLL as it's like for what it's good for.
Yeah,
Yes,
I
and
agree.
that's also exactly what I was trying to get to. I thought about HLL because it would allow you to do better estimates in the cases of AP plus B, because you can combine them and that works fine. But other sketches work well also in the case of intersections. And I'm not sure that Bloom filters can be combined that way. Because Bloom filters are, to the best of my knowledge, HLLs, but only a single bit, and you can't really intersect them.
They're different than HLLs. They're less dense, but they retain more of the. I don't know how to put this. They lose information differently.
Yes.
There are such things as counting Bloom filters. There's there's dozens of like variants of Bloom filters to allow you to do things like intersection or subtraction, set subtraction. I don't know. I don't know. When I first heard about counting Bloom filters, it seemed like it kind of misses the point of what the original Bloom filter was trying to achieve. But I think they're quite popular in industry. So I imagine they're more useful than they seemed to me.
Well, I think they are popular in like people talking about them, but there are actually very few people actually using them in practice nowadays.
I mean, there's a quote.
Doing intersection with Bloom filter is extremely simple, right? Essentially, bitmap. You can combine them as and that's it, right?
Wait, which way is lossy?
I mean, like, if the same element is in both Bloom filters, it will have exactly the same bits set, right? So I think the main problem with Bloom filters for us is that once you get to the low number of bits, it's difficult to actually estimate the. Again, I would propose actually to start with the simplest and then actually do some experiments like how that behaves for different like selectivities and so on.
Yeah.
That's a weird background noise. Is that a pigeon behind you or something?
Oh, that could very well be it. I have some pigeons on my terrace over there.
It's distorted enough that it's hard to tell exactly what it was.
Yeah. But yeah. Yeah, and then how this would fit in Postgres would be probably through the custom statistics for now.
There's a quote from a Postgres person that how does it go? It's been literally months since I mistakenly thought I would be able to use Bloom filters effectively. Something like that.
So Andres has a question in the chat, but I'm not sure like which bigger open questions he's talking about. Like,
I mean, feel free to do such open questions, but I haven't really seen the ones in the threads that I followed, which is limited because I'm new to the community, relatively new. So
Sorry, what's the question? I didn't.
I mean, Andres asked in the chat about like bigger open questions, but I don't know what exactly he means. I don't know, maybe he means like in the, how to say that, in the unconference in general, or I don't know. Okay. Wrong chat.
I think we saw some good things discussed. I understand a lot better now how this combining works and how it would be useful. I think it's really interesting.
For what it's worth, in searching for that quote that I just pasted, apparently Peter also found a data structure called Kaku filters, which are also in the same kind of space as Bloom filters, which might be relevant. But like we were saying, we should probably start with even simpler. And
Yeah, there's about 1 million different variations of Bloom filter or something like that. But let's start simple, I guess.
each of these variants and data structures has different pros and cons and solves different issues. So it's worth really understanding like where the pain points are with a simple solution before we go with a more complicated one.
yeah, well, thanks for all the input. This is quite interesting. I hadn't thought of bitmaps yet, but it's an obvious choice given the sample sets that we use. And yeah, you will probably not hear from me about this for a while, other than maybe on Hackers as an just input, because I have other stuff to work at. See my last talk for today. But yeah, thanks.